parameters and so on. Now that can be proved in many different ways. I don't say that ultra products are needed for it. On the other hand, a good way to get these bounds is to say, well, if there were no bounds, I would sort of use the ultra product to go to a non-standard set of parameters in one of these limit Ds and contradict a uniformity already, a local uniformity I already knew. So this is a very powerful method. Van den Vries is one of the most skillful people in this area. You can use this to derive all sorts of things about uniformity in the theory of polynomial ideals. For example, Bjorn in his lecture yesterday mentioned results of Greta Hermann going back to 1926 on bounds in the theory of polynomial ideals. These are readily obtainable, and many more results than she obtained, by use of this compactness principle. All right, so tomorrow I'm going to have to cover about 947 different topics, something I'll have to give, I think. Okay, thanks.
We can start the second lecture. Bjorn Poonen, third lecture on Hilbert's 10th problem.
Okay, so I'm going to continue talking about Hilbert's 10th problem over Q. Oh, yeah, sorry. So I'm going to continue talking about Hilbert's 10th problem over Q. It's not all clear what the answer is supposed to be. I mean, I would guess that it has a negative answer, that there's no such algorithm, but other people, I think a lot of, well, maybe the majority view is that way, but Barry Mazur and Peter Dyer have both told me that they think there's a chance of a positive answer, so I don't know. Anyway, so here's one fact that's easy to prove. So if you know that Z as a subset of Q is Diophantine, then it follows using the negative answer to Hilbert's 10th problem over Z, that Hilbert's 10th problem over Q has the negative answer. Yeah, but of course, I mean, this is not known. It's not known whether Z is Diophantine over Q. Okay, so how do you prove this? So what does it mean to say that Z is Diophantine over Q? So that means there's some polynomial G, such that the following holds. So that you can tell whether a rational number is an integer by testing whether a certain polynomial, depending on the parameter A, has a solution. So there exists so G is a polynomial in n plus 1 variables, and A is and Z is exactly the set of parameters where the set of A's and Q for which the polynomial has a solution. Okay, so if you assume G is a G is a polynomial. It's one polynomial in n plus 1 variables. Yeah, so okay, so I mean, so I didn't, yeah, so they're supposed, right, G is a polynomial. Yeah, okay, I'm not going to write it. I mean, I've defined Diophantine enough times. Okay, so then the idea is that Hilbert's 10th problem over Z can be encoded. So using this representation of Z, you can encode the Hilbert's 10th problem over Z as a subproblem of Hilbert's 10th problem over Q. So namely, so if you want to decide whether a polynomial over Z has a solution, so f is some polynomial in n variables, this you can encode as follows. So So these are now all in Q to the something. And you use the same equation as before, but now the variables are running over Q. And so you need to put extra equations that will force the coefficients of x to be integers. And that you do by using g. So let x1 through xn be the coordinates of this vector x of variables. So if you put an equation like this, the existence of a y1 that satisfies this equation will force x1 to be an integer, and so on, using the same g, but using a different coordinate x of n for each one. You get a system such that if this system has a solution over Q, then the original system will have a solution over Z, just because these, I mean, this is saying there exists a solution over Q, but then the equations force the variable to be in Q, in Z, and vice versa. So the answers, I mean, the truths of these two sentences are going to be equivalent. But this is, okay, so in other words, for every instance of Hilbert's 10th problem over Z, there's a corresponding, you can encode it as an instance of Hilbert's 10th problem over Q. So Hilbert's 10th problem over Q is more general, so it's a harder problem to solve. But we already know that you can't solve, I mean, there's no algorithm for Hilbert's 10th problem over Z, so it implies that there's no algorithm for Hilbert's 10th problem over Q. All assuming that there is this G. In other words, that Z is Diophantine over Q. Okay, so nobody knows how to show that Z is Diophantine over Q, and maybe it's just wrong. Yeah. There's something more general that would also imply that Hilbert's 10th problem over Q has a negative answer. There are other ways of trying to encode Hilbert's 10th problem over Z into Hilbert's 10th problem over Q. And one would be to use a Diophantine model. So Diophantine model of the ring Z over Q. So let me say what I mean by this. So okay, so this is first of all, it's a Diophantine set. So I'm going to use the Diophantine set in the general sense I defined last time. So it's a subset of the rational points of some algebraic, or some variety, or more generally algebraic set. Okay, so for some algebraic set X, so it's some quasi-projective, not necessarily irreducible variety. But also, okay, so what is it? So that's to say it's a model of Z. You want S to be like Z in the sense that there exists a bijection between Z and S. So I'll call that phi. So okay, so bijection, it's an isomorphism such that, well, to say that it's a model for the Z as a ring, I want to say that I want to be able to express the addition and multiplication on Z in terms of something Diophantine on S. So the way to say that is that, okay, such that if you take the graphs of addition and multiplication, on Z, so those are, so what are, so those graphs are subsets of Z cubed. So the graph of addition is the set of A, B, C such that A plus B equals C. They correspond under this bijection to Diophantine sets in S cubed. In S cubed, you can make sense of what it means for a subset of S cubed to be Diophantine, since S cubed is contained in the rational points on X cubed. Okay, so that's definition. Maybe I should say one thing. if you have a Diophantine model, it's automatic that the function, that bijection phi is recursive in the sense that, well, in the sense that you can a Turing machine can evaluate the function phi. So maybe I should just explain this. So phi is automatically recursive. So how do you compute the values of phi just given that? So sorry, is there a question?
Yes, the issue of the bijection need to be Diophantine. The bijection is any old.
The way I define it, yeah, I mean, maybe, yeah, the way I define it, that it could be any old bijection, but I'm going to prove that it's actually going to be, it's going to be recursive. So, so how do you compute for what phi of 0 is? Well, because this phi is supposed to take the, well, I mean, we know what the graph of addition corresponds to. So you can just search for the unique element of, well, let me call it G plus. So this is going to be the subset of S cubed corresponding to the graph of addition. Okay, thank you. Okay. So the graph of addition. Wow. Okay, so such of the form. So I mean, G plus is Diophantine, so it's going to be listable. It's listable. I mean, you can write a. So it's of the form A naught, A naught, A naught. Because then phi of 0 must be A naught, because there's only one element of Z such that when you add it to itself, you get, there's only one element A and Z such that A plus A is equal to A. So that under this correspondence phi, that must correspond to this A naught. So similarly, you can search for the unique number. You can search for the unique triple A1, A1, A1 that's in the subset corresponding to the graph of multiplication. That will tell you what phi of 1 is. And once you know what phi of 0 and phi of 1 are, you can use the graph of addition to figure out what phi of 2 is, using the fact that 1 plus 1 is 2. And you can continue to generate all the other values of phi. Okay, so now the reason I'm introducing this notion is that I can now generalize that first proposition I mentioned. So first I said if Z is Diophantine as a subset of Q, then Hilbert's 10th problem over Q has a negative answer. And to say that if Z is Diophantine in Q, then Z itself is a Diophantine model, because you just take the identity bijection between Z and, you take X equals the affine line or something, and S equals Z. But now, more generally, I can say, so if there exists a Diophantine model of Z, so over Q, then, again, Hilbert's 10th problem over Q has a negative answer. And the proof is exactly the same. You can encode, using the Diophantine model, you can encode instances of Hilbert's 10th problem over Z as special cases of Hilbert's 10th problem over Q. So, okay, that's all I'm going to, so that's all I'm going to say about that. Let me give you one example. Well, unfortunately, we don't know a Diophantine model of Z over Q either, but if we did, we'd have this this major open problem solved. But there have been attempts to construct Diophantine models. So here's one of the attempts. So if you have an elliptic curve over a Q, then it's known that the set of rational points on it form a finely generated abelian group. And there are many examples where this finely generated abelian group is known. And in particular, there exists an elliptic curve. Okay. Such that the Mordell-Weil group, the set of rational points, is isomorphic to Z. So it just okay. So as an abelian group, and so now you can try to use this. So let me define now a bijection going this way. Let's call this phi. And now you can ask, is this Diophantine set together with this bijection, is this a Diophantine model for Z as a ring? So Diophantine model of Z over Q. So, okay, so what do we need? To show that it is a Diophantine model, you'd need to know, first of all, well, okay, we have everything except for the graphs of multiplication and addition. Now, actually, the graph of addition on Z, that corresponds to something Diophantine on EQ, on EQ cross EQ cross EQ, because the addition law on Z corresponds to some group law on the elliptic curve that's given in terms of rational functions. And anything that's given in terms of rational functions will definitely be Diophantine. So that part is okay. The hard part is getting the graph of multiplication, because the graph of multiplication in this ring Z corresponds to some very funny operation on this Mordell-Weil group. And it's not clear that you can sort of make E of Q into a ring. There's no natural way, at least not natural to an algebraic geometer. There's no natural way to make the set of rational points on the elliptic curve into a ring. It comes as an abelian group, but it's not clear how to do this. Anyway, people are still trying, so maybe it's actually possible.
Yes, for any fixed n, you can make that multiplication by function.
For any fixed n? So the question was,
Multiplication by n, that seems to be that.
okay, what Min Young is pointing out is that for any fixed n, the multiplication by n map is Diophantine. Yeah, so that's true, because you can get, for any fixed n, you can define multiplication by n using addition. You just add a point to itself fixed number of times. Yeah. Okay, so any questions? Oh, yes, question?
Is there a way to get the order defined on the rational points on the elliptic curve? Or order of the integers, It's a more basic question, but
Okay, you mean to have the greater than on,
the graph of the
On-
inequality, for
yeah, so to get the greater than on the integers. I guess I don't know how to do that either.
that's
So the question was, yeah, so to get the graph of the greater than or equal to or something on Z, whether the relation it corresponds to here is Diophantine. And-
much more basic, so it could be a good exercise.
Okay, well, we have lots of students too, so. There's some things you can define. That some other relations. For example, you can look at the set of points whose y-coordinate is between 1 and 2. That's some funny that corresponds to some funny subset of Z. But at least that is known to be Diophantine. But if using such, you can show that using such subsets is not enough to make. If you think of Z equipped with addition and this funny subset, that's not enough to give you something undecidable. So, yeah, so it's not clear what to do. In fact, some people believe that this is not possible to make it. For example, Maser has this conjecture, and we'll show that conjecture is incompatible with this program. So Mazur's conjecture, so which I'll abbreviate by MC for the rest of this talk, says that if X is a variety over Q, then if you take the topological closure of the rational points on X in the set of real points, so, and this you give the topology in the usual way, coming from the usual topology on R. So there's going to be some, well, not quite a manifold, but it's going to be some semi-algebraic set that has finitely many connected components. But now when you take a closure of X of Q, it's not clear what happens. And Mazur conjectures that it always has at most finitely many connected components. Instead of being something like a, I don't know, Cantor set or an infinite discrete subset or something like that. So number theorists are sort of divided. I mean, they don't really know. They don't have any idea whether this should be true or not, just because number theorists have, well, if you look at the big picture of what number theorists have been able to do, they've been complete failures as far as determining what rational points look like on higher dimensional varieties. The one case where they really do pretty much understand what's going on is the case of curves. Actually, even then, we don't really understand things very well. But at least we know the answer. We know that this conjecture is true in that case. So maybe I'll explain this right now. So here's a theorem. So the Mazur conjecture is true for curves. So these are one-dimensional varieties, curves over Q. Okay, so how do you prove this? So first of all, this curve doesn't have to be projective or non-singular, but you can easily reduce to that case, because if you take a projective closure of your curve and then desingularize it, those operations will only change the curve in finitely many points. So, and in this, if you just change, so the rational points will only change by a finite set of points, and that won't change the question of whether there are finitely many components or not. So without loss of generality, we can assume that X is non-singular and projective. And then non-singular projective curves can be classified according to the value of their genus. Okay, well, let me actually make one other assumption. You can assume that X has a rational point. Well, otherwise, this is just true. Okay, so, all right, so now you can break up into cases according to the genus. So the genus is always of a curve is some non-negative integer, and it's been discovered in the past. This is one of the big things in the 20th century, that the topology of the curve over the complex numbers determines the qualitative behavior of the rational points. For example, if it's of genus 0, then and you also have a rational point, then you can use the Riemann-Roch theorem. There's the same proof you use to show that there exists a function, a rational function on X that has a simple pole at one point. And using that function will give you an isomorphism between X and the projective line. And so then, if you take the closure of rational points on P1, then that will just be all the points on P1 over R. That's just because Q is dense in the real numbers. So okay, so that's the genus 0 case. So what happens for higher genus? So genus 1, So then, because I also assume that the curve had a rational point, this means that x is an elliptic curve. That's one of the definitions of elliptic curve. It's a genus 1 curve with equipped with a rational point. And so then you have a group law on the elliptic curve, and then the set of rational points is a subgroup of the set of real points. And what do the set of real points on an elliptic curve look like? Well, it either looks like this or it looks like this. Now, what is this? And there's also a point infinity, which I'm not drawing. But because of that point infinity, it makes topologically, it either looks like a circle or two circles. And as a group, it's a compact one-dimensional Lie group over the real numbers, and there are not too many of those. The only possibilities for what it looks like as a Lie group are, in this case, it's just the circle group, the real numbers modulo z. In this case, it's the circle group cross z mod 2z. So there's this, which is sort of the connected component of the identity, and then there's this other thing with it, which is a coset. And there's a classification of what, well, maybe not of all, well, you can classify what the closed subgroups of this are. So, I mean, not only is x of q a subgroup, but it follows then that its closure inside there will also be a subgroup. And the only closed subgroups are, so maybe I'll say the closed subgroups of the possibilities for the closed subgroups are either finite or if it's infinite, then it either has to be an R mod z, or in this case, in this second case, you can have also the whole thing, which is or R mod z cross z mod 2z. So in all the cases, you can see that these closed subgroups, they always have finitely many connected components. All right, so there are only infinitely many values of the genus left.
So this argument, does it extend pretty easily to a billion varieties?
Yes, actually it does. So the major conjecture is also known for a billion varieties. You can show that any, so what happens then is that the R mod z gets replaced by R mod z to the power of g, where g is a dimension of the billion variety. And this group, the group of connected components becomes some other finite group killed by 2. Okay, so genus greater than or equal to 2. Well, this is hard, but it's very easy if you assume something, namely if you assume Falting's theorem. So Falting's theorem says that if you take the set of rational points on a curve of genus at least 2, then this is finite. So this is what he got a Fields medal for. This was originally called the Mordell conjecture. It was from 1920s, and he proved it around 1983 years. Okay, so well, if you believe this, then if you take its closure, it's going to be the same thing. So it's also going to have finitely many connected components. Okay, so that proves that theorem that it holds for curves. Yeah, but there are not very many other kinds of varieties for which it holds. I mean, it's known to hold. I mean, there's a billion varieties, as Wayne pointed out, but other than that, there's not a whole lot more.
So then you want to know how to prove this without using Falting's anything?
This, I don't know. I mean, I don't. Oh, sorry. So the question was whether you can prove this using something easier than Falting's theorem. Is there something weaker you could use to prove this? And I can't think of anything that would suffice. I mean, if you don't know that there are finitely many rational points, I mean, they could be like, maybe the rational points are converging to something, or or they look like or the closure looks like a Cantor set. I don't know. I mean, I don't know how to rule that out without using Falting's theorem.
There's something like, for example, there was this theorem of Mumford that says that they're very sparse.
Yeah, so that theorem says that they're sparse in the sense of heights, but as far as how they sit in the real points, I don't think it says anything. So okay, Okay, so what I want to show you now is that if you believe this Maser conjecture, it implies not only the finiteness of the connected components for the closure of the set of rational points, but also you get an analogous, it implies the analogous statement for Diophantine sets. So in other words, if you assume that, then if you have any algebraic set, so meaning a variety that's not necessarily irreducible, and you have any Diophantine set contained in the set of rational points. So remember, that just means it's the projection of the rational points from some other algebraic set y mapping down to x. Then if you take the closure of S inside the real points, then this also has finitely many connected components. So okay, so how does this follow from the Maser conjecture? So okay, so well, first I guess you can say that the original Maser conjecture I only stated for varieties, but it's very easy to deduce from that the Maser conjecture for arbitrary algebraic sets, because algebraic sets will be a union of finitely many irreducible components. So, and then these questions will easily follow for that. Okay, so now let's prove this statement for an arbitrary Diophantine subset. So suppose S is Diophantine in some rational points in some algebraic set. So what that means is that there's some variety y, and such that its rational points, well, maybe not a variety, but some algebraic set, such that its rational points give you. Okay, well, let me write it this way. So you have a map from y to x, and then S, by definition, what it means for it to be Diophantine is that S is exactly the image of the rational points from y. So okay, so this is subset, and I can draw the real points here if I want to, and then okay. So and the morphism of algebraic sets from y down to x induces a map on the real points, and it's because f is given locally by rational functions, it's going to be a continuous map of these topological spaces. Okay. So now I need to show that the closure, remember what we're trying to show is that the closure of S has finitely many connected components. And of course what I'm going to do is I'm going to apply the Maser conjecture to y now, because I know that. So, oops. Okay, so we know by the Maser conjecture that if you take the closure of the rational points on y, then that has finitely many components. Fine. So let's say it has n of them. So n is some non-negative integer. So, well then, if you look at the image of this closure under F, then this will have at most n components, because F maps the connected set to a connected set, since it's continuous. And so if there are n connected components here, each one will get mapped inside one of the connected components of this set. And, well, you might have less than or equal to n, because some of these connected components might collapse or map into they might become connected. Their images might connect to each other. But in any case, you won't have any more than n components. Okay, and on the other hand, now if you take the closure of this image, then it's this will also have most n components because the closure of a connected set is connected. So if you have n of them, then the union of this finite union of the closure will be the closure of the finite union. So, and okay, but then by elementary topology, this is the same thing as f if you take the image of the rational points and then take the closure of the whole thing. And that, by definition, was the closure of S. So that's the proof. Okay, so what do we get from this? So that's the end of the proof of this, that Mazur conjecture implies Mazur conjecture for Diophantine sets. Okay, so we have the following statements have the following implications. So there's a statement that Z is Diophantine over Q. Now what I can say right now is that this implies that the Mazur conjecture is false. Because if the Mazur conjecture were true, you could apply it by this proposition. You could apply it to this Diophantine set. And it would say that the topological closure of Z in the affine line over the reals would have finitely many connected components. But obviously, Z, if you take its closure, you just get Z, and it has infinitely many connected components. So the existence of a Diophantine definition of Z would contradict Mazur's conjecture. So I guess Mazur doesn't believe that Z is Diophantine. Okay. Okay, the question was what was Y? So this came from the definition of what it meant for a subset of the rational points to be Diophantine. The definition was that S is Diophantine if there's some algebraic set Y equipped with a map from Y down to X such that S is exactly the image of the rational points from Y. So in other words, Y is going to be some algebraic set, so it's going to be a union of irreducible varieties. So so did that answer the question? Okay. Any other questions? Okay, so there's some other statements I could put here. I could put ask, so suppose I could put ask, instead of this, this is very strong to say there's a Diophantine definition of Z. Weaker is to ask, is there a Diophantine model of the ring Z over Q? And well, it's obvious that this implies this, because Z itself would be, if Z is Diophantine, then it itself would be a Diophantine model. And we already showed that even this weak model of Z in Q would be enough to give the negative answer to Hilbert's 10th problem over Q. Because it would let you encode Hilbert's 10th problem over Z in there. So it has. So now this makes it interesting. What's the exact connection between these two things, the Mazur's conjecture and Hilbert's 10th problem over Q? And nobody knows any direct connection. But you can say a little bit more here. What I want to prove now is that even if you have a Diophantine model of Q, that already gives you a counterexample to the Mazur conjecture. So, and this is, I guess these are all the implications that I know of. So in particular, if the Mazur conjecture is true, this would thwart any attempts to use that elliptic curve as the rational points on this elliptic curve as a Diophantine model. So the Mazur conjecture would imply that you won't be able to define that ring structure on the group of rational points on that elliptic curve that I talked about earlier, the elliptic curve whose set of rational points was free of rank 1. Okay, now this proof is actually a little bit interesting. So let's see. So, well, maybe the other ones are interesting too. I don't want to give the subject a bad name, but okay. So proof of this. Okay, so we're assuming that we have a Diophantine model. Suppose, yeah, suppose there exists a Diophantine model of Z over Q. So using this, you can get, using the fact that non-negative integers are exactly the things that are the sum of 4 squares, this is Lagrange's theorem again, you can say then there exists a Diophantine model also of the natural numbers, which are the non-negative integers, over Q. So I haven't defined this, but you can probably guess what it means. You just take the same definition as Diophantine model for Z and replace Z by N. Okay, and all right. So now this Diophantine model, it could be. I mean, that means it's a Diophantine subset of some algebraic set, but that algebraic set, and this you can do these usual reductions. The algebraic set is a finite union of varieties, and so you can put this. You can put your Diophantine model in a finite union in fact, a finite union of affine varieties if you want to. And you can put those finite union of affine varieties as different layers of a single affine variety. In other words, inside AN cross A1, you can put one variety at sort of Z coordinate 1, another variety sitting in Z coordinate 2. And so in a Diophantine way, you can put an arbitrary. So I guess what I want to say is that if there's a Diophantine model of N, you can also find an affine Diophantine model for N. So let me assume this. So you can reduce to the case where the Diophantine model looks like a subset of affine space. So over Q. So that's Q to the N. All right. So okay. So now, how am I going to construct a counterexample to the Mazur conjecture? Because I mean S. Well, okay. Oh, by the way, so maybe I should say this proposition is due to, it's a theorem of Cornelissen and Zahidi. Oops, no. Yeah, I'm gonna give a slightly simpler version of their proof. Anyway, so so that you can break into two cases. First case is if S is discrete if you view it as a subset in R to the N. In this case, well then so S is a Diophantine set, so what is its topological closure? Well, it might be a little bit bigger than S if S contains some convergent subsequences. But in any case, because S is discrete, each point of S it's by itself a connected component of the topological closure of S. So on the other hand, S is a model of the natural numbers, so S is in bijection with the natural numbers. So S is infinite. So that means that S would be, so that means that the Mazur conjecture is false for S. So for S. And as we said, if the Mazur conjecture, the original Mazur conjecture would imply the Mazur conjecture for Diophantine set. So that would mean that the Mazur conjecture, the original Mazur conjecture would also be false. Okay, so that's the first case. On the other hand, suppose S is not discrete. So what does that mean? That means there exists a non-isolated point. Okay, so I call it little s in S. So that means S, this S is going to be a limit of some sequence of points in S. So there's going to be some sequence in S that converges to S. Sequence of distinct points, not just the sequence S, 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 S. So, okay, so let me introduce the Euclidean norm. So this is just the distance function, be the Euclidean distance on Rn. So the Euclidean norm on Rn. So okay, now the idea is I'm going to have, okay, so here's the picture. So here's the point S. And I know there's some sequence of, there's the S. S contains a sequence of points converging to S. Now I want to, okay, I want to construct a subsequence, a recursive a recursive or at least listable subsequence that'll converge to this. So what I'm going to do is I'm going to construct a sequence M0, M1, dot, 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 of numbers, of natural numbers, such that the image of these numbers, oh, I guess I didn't say what, well, the Diophantine model comes equipped with a map from a bijection between the natural numbers and S. So I'll call that phi. So with, that's part of what you get when you have a Diophantine model. So such that the images of this sequence under phi converges to S. To S. Okay. So, well, okay, maybe I should move. Converges to S. Okay, so here's the picture. So S is here, and I want to construct this. So I mean, the original set S might have points all over the place. It could even be dense in the real numbers for all we know. But I want to construct a subsequence such that this here, phi of M1, some subset. Okay. And this is so. Okay, so, all right, so let me let M0 be 0. So I'm going to construct the sequence by induction. So the next, so that's the base case. For I, at least 1, define M sub I. So I'm going to define it in terms of the previous one as the smallest integer greater than the previous one, so greater than M sub I minus 1, such that its image under this bijection phi is getting very close to S. So within, let's say, 1 over I. So I know that this exists because S is non-isolated. So there are points in capital S that are arbitrarily close to little s. And every point in capital S is phi of some natural number. So if I go to there will be some arbitrarily large integers for which this is close to S. So M sub I exists. So this is a well-defined description of a subsequence of natural numbers. Okay, and it should be obvious that the image of these points is going to converge to S, just because each one is, well, the distances to S are going to 0. So, All right, and now let me let M be the set of all these natural numbers. So this is okay. So that's a subset of N. Now for the key point. The key point is that M is, as a subset of the natural numbers, it's listable. So why is this listable? So in other words, I have to show that there's a computer program that will eventually generate all of these M's. So how do you do it? Well, you know what S, you know you have S, and this bijection phi is a recursive function. That's by the same argument I gave earlier. So you can compute values of phi. So you can just start computing the values of phi, and just use this inductive definition, compute phi of 0, and just test. Compute phi of 0, phi of 1. Take the, phi of 0, you already, 0, you're already taking 0. Compute the first phi of integer. Just keep going until you find one that satisfies this condition. Call that M1, then do the same thing to figure out what phi M2 is. So I think it should be pretty clear that this is listable. But now, if it's listable, then by the DPRM theorem, any listable subset is diphantine. So, we're using a big theorem here, but this isn't just one other use of this key theorem. So it's diphantine, and then, okay, so it's described by some polynomial equations. Now, but you can use phi to transfer those polynomial equations in N to some diphantine relations in S, because the graphs of addition and multiplication here correspond to diphantine relations here. And polynomials can be built up by using addition and multiplication. So you can show, using this, that phi of M is diphantine. It's a diphantine subset of S. Okay, so now on the other hand, what is this? This is a convergent sequence. It's a convergent sequence of distinct numbers, of distinct points. So it's a convergent sequence in R to the N. And so if you take, what happens if you take the topological closure of it, so you'll still have infinitely many connected components then. So it has infinitely many connected components. Okay, so now this contradicts the Mazur conjecture for diphantine sets, because we showed that this is diphantine. So it contradicts the Mazur conjecture for diphantine sets, and hence it contradicts the original Mazur conjecture too, since the original Mazur conjecture implies the Mazur conjecture for diphantine sets. Okay, so, I guess so maybe I'll just end today with an open question. Okay, yeah. So why does this closure? So this is just a fact of topology that if you have a convergent sequence of points in R to the n, then each point, well, except for maybe the limit, will be by itself. Okay, so let me say it this way. So let M is this phi of M is this convergent sequence. What happens when you take the closure? The only new point you get when you take the closure is possibly the limit itself, because all the other points are isolated. Because if you look at it, let's look at one of these points here. If I look at the sequence, all but finally many of the so pick a neighborhood of this sequence that does not contain the limit. Then all but finally many of the elements of the sequence will be outside this open subset. So only finally many in here. And so you can find an even smaller neighborhood that doesn't contain any of those. So yeah, so maybe I've said, okay, I guess it's probably clear now. So so each individual point in the sequence is itself a connected component. well, except for possibly the limit itself. Okay, so the last thing I want to say today, is to mention this open question. So there's an even weaker way, something even, okay, so the strongest thing would be to have Z being diphantine as a subset of Q. So weaker than that would be having Z as a ring embedded as a diphantine, having as a diphantine model. So having it embedded as some diphantine subset in some variety over Q. But you can imagine an even weaker way of encoding Hilbert's tenth problem over Z as a subproblem of Hilbert's tenth problem over Q. And that would be using a diphantine interpretation. So here's a question that I don't know the answer to. So suppose there's a diphantine interpretation. So I'll define this in a second. So of the ring Z over Q. So that means a diphantine set well, maybe I'll just say it loosely. I don't want to. Diphantine set modulo a diphantine equivalence relation. So as I said before, relation is diphantine if and only if when you consider it as a subset of whatever as a subset of the Cartesian product, if it's diphantine. So modulo a diphantine equivalence relation. Okay, so diphantine set modulo equivalence relation that looks like the Z. Okay, maybe looks like is not very rigorous, but I think you can probably imagine what I mean. There should be some map from S to Z that induces a bijection between the equivalence classes here and Z, and then if you pull back the graphs of multiplication and addition on Z to subsets of S cubed, then those should be diphantine subsets. Okay, so now the question, I haven't said what the question is. The question is, would the existence of such a thing, would that also give a counterexample to the Mazur conjecture? So that's what I don't know. Because it's conceivable that Mazur could be right and Hilbert's 10th problem could still have a negative answer, and this would give you another way of giving a negative answer to Hilbert's 10th problem over Q, because it would let you, again, encode Hilbert's 10th problem over Z as a subproblem of Hilbert's 10th problem over Q. But then it might not have to contradict Mazur. So I'll end here, and next time I'll talk about Hilbert's 10th. Well, we don't know how to give a negative answer to Hilbert's 10th problem over Q. We do know how to give a negative answer for Hilbert's 10th problem over Z, and there are lots of rings in between where you invert some of the primes of Z, but not all of them. And so next time we'll try to see how far up we can go and still get a negative answer. Okay, so thank you.
Are there any questions? Yeah, Brad.
Can you comment on other approaches to code problems into Hilbert's 10th problem over Q? This is all focused on one direction, code Hilbert's 10th problem over Z into Hilbert's 10th problem over Q. Presumably, other problems that are inside of those problems known also.
So the question is, can you encode other problems other than Hilbert's 10th problem over Z? Is this right? You want to encode problems other than Hilbert's 10th problem over Z, encode them in Hilbert's 10th problem over Q. And I guess the idea is if you could encode some other problem that you already know a negative answer that you can't solve, could you use that to show the undecidable, to show that that there's no algorithm for Q? I guess that's the spirit of that's right. So, I mean, yeah, that's certainly a good idea. I mean, in fact, the analog, the function field analog, where you replace Q by say a rational function field over a finite field, so like FP round bracket T. For that, it was well, okay, I guess it was kind of there. Okay, but anyway, there was originally it was some other structure that was known to be undecidable that was embedded into the arithmetic of this field, and it was the embedding of that structure into there that was used to prove that the Hilbert sense problem over that global function field had a negative answer. So yeah, so that might be I mean, people have struggled so long to embed Hilbert sense problem over Z inside Hilbert sense problem over Q and not succeed. Maybe it's a good time to start looking for other ways to prove it's undecidable. Yeah, it's an excellent point.
Any other questions? Yeah, Florian.
What about the invariance of this Maser conjecture? If you take that closure also.
Okay, so the question is, how about p-adic variance of the Maser conjecture? So I assume what you mean is instead of taking the closure of the rational points in the real points of x, in x of r, take the closure in x of qp, say, where x of qp also has a topology coming from the topology of qp. And Maser himself actually proposed an analogous conjecture. And it's a little bit different. It's a little bit different to state. I mean, you can't state in terms of connected components very so well because it doesn't work so well since QP is totally disconnected. But there is some other. He figured out some other way to express something that's sort of in the same spirit. I don't think I'll state it right now, but I can explain to you afterwards.
No counterexample to that.
Yeah, no. As far as I know, there's no counterexample to that either.
Any other questions? Oh, sorry.
What is your guess concerning the Maser?
My guess concerning the Maser conjecture? So you're going to put me on the spot? You forced me to answer? I mean, if you forced me to guess, I would guess that it's false.
Can I ask a question?
Yes, you can ask a question.
I mean, one could strengthen Maser conjecture to sort of say that the topological closure is something like semi-analytic or something a bit more